Section 6.1, Greatest Common Factors and Grouping. So in this section, we're going to take a look at the opposite of what we were doing in Chapter 5, where we were distributing and multiplying. We're now going to go in the opposite direction and take an expression that is already fully expanded and get it back into what we call factored form. So it's kind of the opposite of distributing. In a sense, we can think of it as dividing, whereas distributing is multiplying. But it's a little bit more than dividing, as you'll see here shortly. So kind of review the idea of distributing. If we had an expression like this, where we have 3x times the value 5x minus 2, we would have to distribute the 3x into that parenthesis, which would give us the expression 15x squared. When we do 3x times 5x, and then 3x times the negative 2 would give us a minus 6x. That again was distributing, going in the direction where we would multiply. What we're going to be looking at in this section now is if we were given a problem like 15x squared minus 6x. So where our answer in a distributing problem is the actual expression we're given to start with in a factoring problem. We'll be asked to factor an expression like this, and factoring really just kind of means what could we divide out of each of those terms. So in this case, we get back to what we started with in the distribution problem. If we had pulled a 3x out front, what would we need to multiply back into to get back to the 15x squared minus 6x? And that would lead us to the 5x minus 2. So we're going to learn how to do that, that second problem there. We already know how to do it the top way. We're going to learn how to get from an expression like this into an expression factored like that. So the first way we typically learn when we talk about factoring is how to factor by pulling out a GCF, our greatest common factor. So we first need to discuss what exactly is a GCF. So GCF, greatest common factor, it's the largest factor that multiple terms or multiple numbers have in common. That's why it's called not just greatest factor, but greatest common factor. They all have to have this factor in order to be a GCF. So one way to do this when you're given multiple numbers is to make a list of values, and that way you make sure you exhaust all possibilities so you're not forgetting any factors. So 12, for example, what numbers multiply to give you 12? Those will all be factors of 12. So we can start with 1. Okay, 1 times the number 12 will always be factors. 2 will also divide 12 evenly. 2 times 6, so 2 and 6 are factors. 3 times 4 gives you 12, so 3 and 4 are factors. And we know we've hit all possibilities when our lists, as you see the left column, values are increasing while the right columns are decreasing. Well, they've kind of met each other here now. The next number in the list would have been 4, but we already see that on the right side of this table. So we just start repeating factors at that point. So we know we've hit all our possibilities with 12. Then we can look at 36. 1 times 36 gives us 36. 2 times 18. 3 times 12. 4 times 9. 5 will not go in cleanly, but 6 will. 6 times 6 will give you 36. And again, our two lists have actually met each other in this example. 6 on the left side, 6 on the right. The next factor would be 7. But if we would have hit a 7 as a factor, we would have seen it here in between the 9 and the 6 on the right-hand side. So because these numbers are getting bigger, these are getting smaller, once we meet each other, we know we've hit all possible factors. And then last, let's make the list of factors for 40. 1 times 40. 2 times 20. 3 is not a factor. 4 is, though. 4 times 10. And since 40 ends in a 0, we know that 5 should be a factor. 5 times 8. 6 and 7 both are not factors, so 40, they won't go into 40 evenly. So the next possibility would be 8, and we already have that listed. So looking at our 3 lists now, what is the largest factor that's common to all 3? So it has to be in all 3 lists. and that would be the factor of 4. So here we would say our GCF, our greatest common factor, is 4. Okay? So that's just finding the GCF with numbers. You might be able to do that in your head for a lot of these. You might not have to make a list of factors like this. I'm just showing you if in case you need to, that's how you could do it. So what if variables are involved? Not just numbers, but expressions with variables, maybe even multiple variables. Well, to kind of stick with the same definition, a GCF is going to be the largest, because greatest, it's going to be the largest power of the exponent, the largest power that is common to each variable. Okay? So how will that look? Well, we're trying to find the GCF of 10x to the third, 5x squared, and 20x to the fourth. Okay? We can find the GCF of our numbers, our coefficients, the same way we were just finding the GCFs of the numbers in the example above. Trying to find the GCFs of the coefficients. We have 10, 5, and 20. We're trying to find the largest factor of each. What's the largest number that will go into all three of those? Well, you always want to start with your smallest number, in this case the 5, and start thinking about the numbers that will go into it. Because if it's a GCF, it can't be bigger than your smallest number, otherwise it won't go into your smallest number. Well, the only number that goes into 5 is going to be 5. It also goes into 20 and 10. So since 5 will go into all three of these numbers, 5 is our GCF. Now, how do we deal with the variable portion? Well, we have an x to the third, we have an x squared, and we have an x to the fourth. So we can think of this as x to the third, x squared, and x to the fourth. So we could write this out as repeated multiplication. Okay. X to the third means 3 factors of x, x squared means 2 factors of x to the fourth means 4 factors of x. Oh, I didn't realize we're off the screen here. So, what we now want to look at then is what is the largest amount of factors of x that's common to all the lists. So following it up the same way we did kind of before, 3 factors, 2 factors, 4 factors, they all have at least 2 factors of x. Okay. It has to be common to all 3 lists. So we have 2 factors of x that are common to all 3 lists, so we can take 2 factors of x for our variable portion. So for the GCF of the variable, it's going to equal x squared. Okay? Because each term has at least 2. Alright, so we can look at one more example of dealing with variables as well as the coefficients. Oh, actually, sorry, we didn't write the final answer there. To write our final total GCF is we put the variable portion together with the coefficient portion. So we would say our total GCF is the coefficient part, the 5, together with the variable part, the x squared. So 5x squared would be our, final answer to our GCF problem. Okay. So we now look at the next example. So we have 3 new expressions: 6a squared b to the 5th c, 9a to the 3rd b to the 4th, and 15ab to the 3rd c squared. So let's set this up the same way. First, find our GCF of our numbers. So we have 6, 9, and 15. We want to consider what's the largest number that will go into all three of those. So start with your smallest coefficient, 6. Think about numbers that go into 6. The largest number that goes into 6 would be 6, but 6 will not go into 9, nor will it go into 15. Next biggest number that goes into 6 would be 3. 3 will multiply into 9 and into 15, so 3 is going to be our GCF of the coefficients. So then we want to look at our variables as we did in the example above. We have a squared in the first term, a to the third in our second expression, and then a single a in the third expression. So remember, we can only take what all of the expressions all have to have at least that amount in order for us to take it for a GCF. So it ended up being, in the last example, it ended up being the least amount of, the least power, smallest power of our variable. So in this example, same idea. So we have a, which another way of saying a would be a to the first. Well, they all have at least one power of a then. So that's what we have to take, is a single power of a. We can then consider our b terms. B to the fifth. The second expression has b to the fourth. The third has b to the third power. Well, all of these three expressions have 3 powers of b. All have at least 3 powers of b. So we can take 3 powers of b for our GCF. And then lastly, we have a single power of c, no c's, and then 2 powers of c. So again, because it's a common factor, it has to be common to all 3, we would have to take the least amount, which isn't 1c. The least amount is going to be the middle here, no c's. So writing our total GCF, is going to equal coefficient 3, single power of a, 3 powers of b, and then no c's. So 3ab to the third. Okay. So that's finding a GCF. And the next examples on the next page, we're now going to look at actually factoring out a GCF, which the first half of factoring it out is finding it. So we kind of learned how to do half of these next problems. Now we have to learn how to do the other half. Alright. So factoring by dividing out a GCF. Alright. So we have the expression 14a squared minus 28a plus 7a to the third. Our first step in all of these problems where we are going to factor out a GCF is to first find the GCF. So in this expression, we once again look at our 3 terms. 14a squared, a minus 28a, and a positive 7a to the third. So our GCF here, as we were just doing on our last problems, 7, 14, and 28, what's the largest number that will go into all 3 of those? That's going to be 7. And then what is the, power of a that is common to all 3? Well, they all have at least one single power of a. They all have at least a single a in them. So a squared, single a to the third. We can take a single a for our GCF then. Okay. So there's the first step. are finding our GCF, which is 7a. The next step is then to divide the GCF out of each term. Because if you remember from the very beginning of the lesson, we want to be able to write this expression in what's called factored form, where we will write this GCF out front and then open up a parenthesis to show what we would be multiplying it by to get us back to this expression. So we write the 7a out front of a parenthesis and then divide it out of each term of the 14a squared minus 28a plus 7a cubed. Okay, so we take that and we write a 7a out front, and in order to write a 7a out front, the opposite of distributing it in to multiply would be we would be dividing it out of each of these three terms. Okay. So we could go through here and actually simplify using the quotient rule. 14 divided by 7 gives us 2, and a squared divided by an a to the first. We subtract the exponents, leaves us with a single a, minus 28 divided by 7 is 4, and the a's essentially divide each other out, plus 7 over 7 is 1, a to the third over a to the first. We subtract exponents and we get a squared. So 1a squared, or just a squared in that part. Okay. So again, the a's kind of cancel each other out, just as the 7's factors there cancel each other out. And keep in mind, this right here, this is your answer in this problem. Okay. Sorry, we need to close the parenthesis. That right there is your answer. We pulled out our GCF, we factored it out front, and we showed what would be left inside that we'd have to multiply 7a by in order to get this 14a squared expression that we started with. So how do we check? Well, we can check by distributing. Multiply the 7a back in to see if it gets us back to what we started with. Okay. So doing so, we'd have 7a times 2a. That's going to give us 14a squared. So first part, check. 7 times a negative 4 gives us a negative 28. And then an a times, well, no other a's, keeps that a single a. And then last part, 7 times no coefficient is just a 7. A times a squared gives us a to the third. So you see from looking at it this way, multiplying it back, distributing back in, it checks. So once again, this whole process of factoring is just distributing, but in the opposite order, in the opposite direction. Okay. So we have two more examples we can try doing the same thing with. We want to factor by pulling out the GCF. So let's use our same steps, our same process. First step is going to be to find a GCF. So GCF equals, we are coefficients, we have 25, 30, and 15. The largest number that will go into all three of those is going to be 5. Then we have x squared, no x's, and x to the fourth. So for our GCF, we have to take no x's. It's going to be, because it has to be common to all three. If one of the terms doesn't have an x, we can't divide out an x from it. Then we look at our y's. Y to the third, y to the fifth, y to the seventh. They all have at least 3 powers of y. So 5y to the third is going to be our GCF. So step 2, take that GCF, write it out in front of a parenthesis, and then inside the parenthesis divide it out of each of these three terms. So 5y to the third, and then we have 25x squared y to the third over 5y to the third plus 30y to the fifth over 5y to the third minus 15x to the fourth y to the seventh over 5y to the third. Okay. So now, actually divide it out of each. We end up with 25 divided by 5 is 5. X squared up top, so we don't subtract any powers from below. Y to the third over y to the third, that will cancel out our y to the thirds. Then we have 30 divided by 5 gives us a positive 6. 5 minus 3 gives us a new y power of y squared, is 2. And then lastly, 15 divided by 5 is 3, but it is subtraction here, so minus 3. X to the fourth, this is going to stay in x to the fourth. Y to the 7 over y to the third, we subtract exponents and get y to the fourth. Close our parenthesis. That right there is our answer. And the third step would be to check that. So once again, we could distribute that back in order to confirm that we have the correct value. So again, 5 times 5 gives you 25, x squared y to the third. 5 times 6 is 30, y to the third times y squared gives you y to the fifth. 5 times negative 3 is negative 15. We have x to the fourth already. Y to the third times y to the fourth gives you y to the seventh. Okay. So again, step 3, distributing checks. Okay, last expression now to factor, and this is a little bit trickier, a little bit different, but it still kind of works the same. What you want to catch in this, it's kind of already in somewhat of a factor form, but both of these terms have an r plus 2s as a factor. Okay, so since they both have that in common, we can pull that out in front of each. Okay. So for our GCF, we can take an r plus 2s. How many can we take, though? The first term had 2 of them, power of 2. The second term had 3 powers of r plus 2s. So we have to take what is common to both. They both have at least 2. So we can take 2 for our GCF. Okay. So there's step 1. Step 2 is then to divide it out of each, divide that GCF out of each term. So I guess how we write that is r plus 2s squared, and then we open up a big parenthesis and divide that out of this term and this term. So we had p parenthesis r plus 2s squared over our GCF r plus 2s squared minus q r plus 2s to the third all over our GCF r plus 2s squared. Okay. So simplifying that up, well, we have 2 powers of the same factor, r plus 2s over 2 powers of r plus 2s. Those are going to divide each other out. Whereas over here, we have 3 powers, and we're going to be over 2 powers. It's kind of the same idea where we subtract the exponent. So we're going to take away 2 powers here, and we're going to lose 2 powers here. It leaves us with 1 single power of r plus 2s. Okay, so simplifying that, we end up with r plus 2s squared on the outside, and inside the parenthesis we have a p, the whole rest of that canceled, minus q, parentheses, and over here we're just left with a single r plus 2s. So at this point you probably would be expected to distribute this negative q here into that parenthesis and just clean up the second parenthesis here. So for our final answer, r plus 2s squared, parenthesis p, minus q times r is going to be minus qr, and then a negative q times 2s is going to give you minus 2qs. And that right there would be your final answer. And I'll leave it up to you guys to go back and check that one by distributing back in. Alright, that is all of the factoring by dividing out a GCF I'm going to do in this section. We do have to look at one more page of notes, which we'll do in the next video to talk about grouping.